Thank you very much for attending my presentation. So today I'm excited to tell you a bit about the work I did last year for my master thesis on the statistical framework of safe testing, and specifically on implementations for the 2x2 Contingency table test and the Cochran-Mantel-Haenszel test, the stratified extension thereof. So the work I did last year I'm still continuing, as after my master thesis I continued as a PhD student at the same group, so I'm still supervised by Peter Grünwald. So for today I hope to, in the upcoming minutes, give you a bit of an introduction on safe testing, and thereafter we'll talk about the implementations I made. So let's first go over some preliminaries. In a 2x2 contingency table test, we aim to compare two strategies, A and B. So in two groups treated with one of the strategies, we observe the numbers of successes and failures, and we aim to decide if there is a difference in the success fractions between the two groups. Now, in the title of my thesis, you can also read something about the Cochran-Mantel-Haenszel test, which is just an extension of the 2x2 contingency table test where we stratify according to a third variable. All the things I'm going to tell you about the 2x2 contingency table test in this video can also be extended to this setting, but to keep this presentation simple, we'll focus on the 2x2 case. So would we want to do this 2x2 contingency table test just once on one data set? The approach would be relatively straightforward. However, we would like to evaluate if the groups are different as data come in real time. And we want to be able to stop the experiment as fast as possible to be able to draw a conclusion with regard to what strategy has to be considered superior to the other one as fastly as possible. And we also want to do this while keeping a guarantee on the probability of making an error. Would we, for example, calculate a p-value with Fisher's exact test at every time point, we can see that the error probability, so the chance of wrongly deciding that the groups are different, will eventually go to 1 as we collect more and more data over time. This is where safe tests come in. In a minute we'll go over how safe tests can deal with real-time analysis, but let's go over the definition first. So safe tests use random variables called e-variables, or e-values, and they represent evidence for a hypothesis in the data. When e-values are high, we have a lot of evidence for our alternative hypothesis, and when they are low, we don't. So we can view e-variables and safe tests as a bid on our alternative hypothesis. So we're making an investment on the alternative hypothesis that strategies A and B are different. Let's say we bid €1. So when there is in reality no difference between the groups, so the scenario you see on the left hand side, we expect to lose our investment, and this is a direct result of the definition of e-variables. Those are namely every random variable that satisfy the equation on the left. So all random variables that have an expectation of at most 1 under the null hypothesis. However, when we see that the e-value of a hypothesis test is high, we can reject the idea that the strategies have equal results. And we can use the rejection rule that you see on the right hand side of the screen. So if the e-value is higher than 1 over alpha, we can reject the alternative hypothesis. And then we have a guarantee on the probability of wrongly concluding this at level alpha. So the nice thing is that we can do this for multiple experiments, and that we then can multiply the e-variables collected in those experiments. And the resulting number is still an e-variable. And this is how we can optionally continue data as they come in real time. So this multiplying of e-variables, which is also called optional continuation, can be done with all safe tests. And some special safe tests can even handle optional stopping, which you see illustrated here. So at every time point where a data point comes in, we perform a hypothesis test. And when the test is significant, we stop and report our result. And when the test is not significant, we continue collecting data. And as you can see on the right-hand side, when we do this with the safe tests, the probability of wrongly concluding that A and B are different remains bounded. However, when we try to do this with the p-value test, you see that the probability of wrongly concluding this keeps increasing as we collect more data points over time. As we just saw, a lot of random variables satisfy the criterion for providing a safe test, as the only criterion is that the random variable should have an expectation of at most 1 under the null hypothesis. But how do you now choose a good safe test for your alternative and null hypothesis? This is where the GROW criterion comes in. GROW stands for growth rate of profit optimal for a subset of the alternative hypothesis, even in the worst case. So in other words, this means that given a subset of my alternative hypothesis that does not include the null hypothesis, we can put a guarantee on the expected growth of the E variable as we do experiments over time. So this is great. If the data are really generated by a distribution in my alternative hypothesis, I have a guarantee that I will make a certain profit. As it turns out, these GROW E variables are special Bayes vectors with special priors that are not really Bayesian and can often be derived analytically or numerically. As a first option for defining this subset, we could take the set of all distributions where there is a certain minimal absolute difference between the success rates in groups A and B. Such a design will often be relevant in the medical field, where treatment effects of a drug will only be considered clinically relevant when it crosses a certain threshold. So a second and perhaps more neutral option would be to design this subset with only promising distributions with respect to profit. So in this second version, we include all distributions in our subset that would yield a minimal expected growth of profit. Would we design a GROW safe test just for them? So this involves calculating the expected growth of profit for all of the distributions in the alternative hypothesis, and this is done through finding the reverse information projection of each of these distributions onto the null hypothesis. For my thesis, I implemented GROW safe tests for both scenarios and compared them with respect to their performance. So first, for the difference-based test design. It turned out that an analytical definition for the GROW safe test existed for this design. It's very easy to compute and not computationally intensive at all, so very quick to use. It also turned out that this safe test is a test martingale, so this means that we can test and make a decision at any moment in real time. And this really offers a lot of benefits with regard to time and effort. As you can see here in the graph, you can see that often when we use the safe test with the optional stopping in real time, we can stop earlier than when we would use Fisher's exact p-value. For the second design, the profit growth based test design, such an analytical solution could not be found, so this safe test has to be defined numerically for each sample size through optimization. Also, this safe test could not be proven to be a test martingale, so we have to be slightly less flexible. If you would want to use this safe test in real time, you'd have to define blocks of data that you are going to calculate an E variable for, and those can then be multiplied as data come in over time, so slightly less flexible. However, this safe test might be preferable to the difference-based safe test. In some situations, as you can see here illustrated in the figure, we can see on the x-axis the number of successes in group A, and on the y-axis the number of successes in group B. And we see that towards the edges, so with the more extreme observations, the profit growth based E variable offers a bit more power. This was what I wanted to present to you today about my master thesis. If you want to read more about safe testing, you can take a look at the resources I've put on the screen here. And if you have any further questions, please don't hesitate to contact me at my email address.